So in this video, we're going to talk about Gaussian elimination, which is a method that is often used to solve a linear system of equations numerically. This is a method that MATLAB will use to provide a solution to a linear system, for example. It's a nice method because it's generic, it's standardized, and it's generic, so therefore it's easier to program. To get to the understanding of this method, we're going to first define what we mean by an augmented matrix, and then we're going to use this augmented matrix in the definition of the forward elimination procedure, which is a way to take your linear system and rewrite it in an equivalent form so that it's easier to solve, and then it's finally solved with a method called backwards substitution, also known as plug and chug sometimes. We'll also talk about strategies for avoiding division by zero throughout this process, which is also known as pivoting in this domain. We'll talk about linear systems which are harder to solve. We'll talk about the condition number, and we'll also talk about the computational cost of these procedures. So here is again our linear system of equations, which again is a set of equations that are linear in the following sense, that the unknowns, which in this case are x1, x2, x3, all the way to xn, they appear linearly, meaning there is no x squared, there is no sine of x or anything like that. Rather, at most there is a number. For example, here it's denoted as a11, a12. At most there is a number that multiplies these unknowns, right? So in that sense, this is a linear equation, and we have a set of equations. And on the right-hand side, we standardize so that there's just a number here, no unknowns, right? So we have a set of equations, and as we saw in the previous video, we can take the set of equations and rewrite it as a matrix of known coefficients, a11, a12, and so on. A vector of unknowns equals a vector of known numbers on the other side. In other words, a times x equals b. A times x meaning matrix vector multiplication. So before we actually get into the solution of a linear system, we have to remind ourselves that not always a linear system has a solution. Sometimes there is no solution that it will exist. Sometimes there is an infinite number of solutions that exist, and sometimes there may be a solution that exists, but it's hard to find. So as we already talked about, a 2-by-2 linear system of equations, in each equation in that system, each equation can be viewed as the equation of a line. Right? And so the linear system will have no solutions when the two equations in a 2-by-2 system imply different parallel lines. In this case, there is no intersection between these two lines, so there is no point x1 and x2 that belongs to both lines at the same time. Conversely, these two lines, for these two equations may imply two lines which are the same line. They lie exactly on top of each other, in which case we have an infinite number of points that belong to both line 1 and line 2, so an infinite number of solutions. In both these cases, the matrix that is used to represent this linear system is called singular. We can have a solution, but sometimes the solution may be hard to compute, and this is usually the case when the lines in a 2-by-2 system, for example, are close to being parallel, in which case a slight numerical mistake throughout these calculations may change the answer by a large amount. In this case, we call the system ill condition. So with that out of the way, let's talk about this definition of what we call the augmented matrix. Again, here is our linear system, and here is equation 1 or row 1. Corresponds to equation 1, row 2, all the way to row n. So in this case, we're looking at a square system, the same number of unknowns and the same number of equations. As we saw, it's most common to rewrite the system as a matrix times a vector of unknowns equals a vector, and we're going to build what we call the augmented matrix by simply taking this vector of values b on this side and just concatenating as an extra column on this matrix A, right? So here's the result. This is called the augmented matrix. This is done so that we can do some easier bookkeeping, right? We're going to now, we don't have to really keep the definitions of x1, x2, all the way to xn, because these are sort of implied by the problem definition. We don't have to keep writing them, right? We know there will be n unknowns in an n by n system. And so what we're going to do now is define operations that are going to be performed equation by equation or row by row in this augmented matrix in such a way as to simplify it so that we can use a simple algorithm to backward substitute and find the actual value of the unknowns. How are we going to do this? We're going to take advantage of a few basic, I would argue, commonsensical rules about what we can do to an equation without changing the solution of the system of equations, right? First thing to note, let's say we have a 2 by 2 system of equations. Here's equation 1 and here's equation 2. It doesn't matter as far as the solution is concerned if we write equation 1 first and equation 2, or we switch the order. It doesn't matter because the x1 and x2 that satisfy both equations at the same time will be the same as the original system. So we're allowed to switch the order, essentially swap two rows of the augmented matrix. Likewise, we can take any equation, either equation 1 or equation 2, and multiply it by some number that we'd like to multiply it by. For example, we can take equation 2 here and multiply by 2. And replace the equation 2 by the same equation multiplied by 2. The same thing that I said for the change of order applies here. The solution, that is the value of x1 and x2 that satisfies both equations at the same time, will not change. Finally, we can add two equations in a linear system and replace one of these equations by this addition, and the same can be said here, that the solution x1 and x2 will not change based on this addition. So here's an overview of Gaussian elimination. So here is our augmented matrix, right? We've taken a 3 by 3 system of equations. Again, we removed the unknowns because those are implied, and we concatenated the b vector on the other side, so now we have, this array essentially. The first step in Gaussian elimination is to use the operations we just talked about, right? Multiplying the line by the same factor, adding the same number to both lines and so on, to both sides of the equation and so on. We can use these tricks to rewrite this system of equations into another system of equations where the values below the diagonal will be 0. So the solution to this system equation and the solution to this system of equations, again, are the same. So we can solve either. This one is easier to solve, for example, because the value of the unknown x3 will just be given by b3 2 prime divided by a33 2 prime. Once we know the value of x3, we plug it in here, and then we find the value of x2 very simply. We take this term, subtract it to the other side, and solve for x2. Likewise, we know x1 and x2 and x3. In this case, we plug it up here, and we solve for x1. So this is known as backward substitution. So let's look at a quick example of how to do this forward elimination procedure. We have here a system of equations, equation 1 and equation 2, right? And so we're going to now leave equation 1 as is, and we're going to modify equation 2 so that the first term here will be 0, right? And again, we're going to modify by either multiplying both sides of the equation by the same number or adding the same number to both sides of this equation too. So here's one trick. Let's take equation 2 and replace it by equation 1 minus 2 times equation 2. So let's do this, right? So let's write equation 1 here on top. That's going to be 3x1 plus 2x2 equals 8. And now let's write here at the bottom 2 times, so here's equation 1 again. And here's equation 2. So sorry, this is going to be minus 2 equation 2, right? So this is going to be minus 3x1. Minus with a minus becomes a plus, so that is going to be plus 2x2. And of course, we have to do the same thing to the right-hand side over here. So that's going to be minus 2, minus becomes a minus, so that's going to be 2, right? And again, we're going to add these two terms, as we just stated over here. And so this result will be 0, x1, right? Minus 3 with 3 becomes 0. This is going to be plus 4, x2. And this is going to be 10. Right? So we're going to now take this result and replace equation 2 by that. So let's rewrite our linear system. So this is going to be equation 1 will remain the same as we had before. 3x1 plus 2x2 equals 8. And now the modified equation 2, which we call equation 2, let's say prime, right, will be 0x1 plus 4x2 equals 10. And in this case, we're done. We have performed forward elimination. Because as you can see, now we take this matrix out, right? So we rewrite this in standard form. We have 3, 2, 0, 4. And of course, we're going to add our extended matrix, augmented matrix here. So here's our thing. And you can see for this part of the system, the numbers below the diagonal are 0, which is what we said we wanted to do. In this case, we accomplished it. So now we can apply the method of backward substitution, right? So from equation 2 prime here, we can now solve for x2 because there was a 0 there, so there's only one unknown variable there. So x2 here will be equals to 10 divided by 4. And now once we know x2, right, we plug it into equation 1 over here. And now we have 3x1 plus 2 times 10 divided by 4, and that has to be equal to 8, right? So once we have this here now, of course, we can just move this to the other side and divide the whole thing by 3, and we have our solution. So we can do the same thing with a 3 by 3 system. Right, so let's rewrite an equation here for a 3 by 3 system. So let's say x minus 3y minus 2z will be equal to 6. And let's say this is equation 1. Equation 2 will be equal to 2x minus 4y minus 3z equals to 8, and equation 3 will be equal to minus 3x plus 6y plus 8z equal to minus 5. So let's take a look at how to solve the linear system, right? So let's apply the forward elimination procedure here in this case. So step 1, we're going to now work on equation 2, right? So we're going to leave, the strategy is to leave equation 1 the same. And now we're going to work on equation 2 and try to eliminate equation 2 and 3. And we're going to try to eliminate the value of this value. We're going to try to set to 0, and this also we're going to try to set to 0. Right? So here is one idea. I mean, there's no unique solution here. In fact, oftentimes there are many ways to do this. But one way to do this we can do is we can take equation 2 and replace it by minus 2 equation 1 plus equation 2. Right? And so and for equation 3 we can replace it by 3 times equation 1 plus equation 3. So if you follow the same procedure that we just did in the previous example, and you substitute, now you will have a new system, which we'll call, again, equation 1 remains the same, right? So we'll have x minus 3y minus 2z equals 6. Equation 2 prime now, I write equation 2 prime to make sure that we understand this is a different equation than equation 2, right? So this is going to be, if we perform this operation here, we substitute the original equation 2 by this modified version. So this is going to be 2y plus z equals minus 4. And equation 3 prime, again, because we replaced the original equation 3, it's going to be minus 3y plus 2z equal 13. So our original system was here, and now we have rewritten it over here. The solution of, that is the points x, y, and z that satisfies all these three equations should be exactly the same as the x, y, z that satisfies these three equations. So the solution hasn't changed, but you can see that we have rewritten the system a little bit. Now we have done, right, we have set these variables here to be 0x, 0x, right? So that's what we have to do now, is work on this particular variable. Let's set that to 0 as well by performing these legal operations. So let's replace equation 3, say, with 3 equation 2 plus 2 equation 3. Right? So if we do this, we're going to end up with a new system now. So the first two equations won't change anymore, right? We already worked on them. So the equation number 1 is still x minus 3y minus 2z equals 6. Equation 2 will remain as before, so it's going to be 2y plus z equals minus 4. And now equation 3, as you'll see, will become 7z equals 14. So here's our third version of the system. And from here, we can see that z is equal to 14 divided by 7, right? Once we obtain z, we plug it in here, and then we can solve for y. Once we have y and z, we plug both the numbers here, and we solve for x. And that will be the business of backward substitution. So how do we write this in a more standardized form for a generic linear system, right? What is the general strategy to follow here? So you work on rows of this matrix, one row at a time. So for example, you start and you leave row 1 or equation 1 unchanged, and you work to zero out all the elements of A21, A31, and so on, all the way to N1 below the first pivot point, right? So what does that mean? Equation 2 or row 2 now will become equation 2 prime or row 2 prime, and you will note that all you have to do is subtract A21 divided by A11, so A11 is our pivot division point, times equation 1. If you perform this operation here, what will happen is this guy in the new version of the equation will become 0. Of course, you do this same for row 3, row 4, and so on, right? So you keep the same division point A11, and you divide, A31 by that number. But otherwise, all that's changing is that from row 2 here becomes row 3 or equation 3, right? You can see, and this the coefficient here also changes, but you can see how this is easier to program, right? And you repeat the entire process for all of these numbers. And that's step 1. Now for step 2, now you have replaced each of these equations here by their prime versions, right? So now all of these elements here have become 0. Now you do the same thing for these guys, for these guys here, right? You leave A22 as the pivot point, but you apply all of the same ones from there. And the procedure is identical, right? But instead now we're playing with this value, and so on. And you keep doing this all the way until the very bottom, or you do it n-1 times, right? Because you'd skip the first one, so you have 1 times less than the size of the system. But by the time you repeat this enough to get to the bottom, you end up with a very simple equation here. And all you have to do to get the last value of your unknowns is divide bn minus 1 here by a and n to the n-1. Right? So, and that's the general procedure for what's called Gaussian, the forward elimination part of the Gaussian solution to linear system of equations. Now, once you have performed this part, you perform the backward substitution, which in this case we already talked about, right? We simplify the linear system to be 0 below the diagonal, so we can get x3 to be simply b3 2 primes divided by a33 prime, right? So this is what we're saying over here, this part of the formula. And then once we have x3, we plug it in here, and then we only have to solve for x2, right? And here is the solution for that formula, where the sigma here is summation, right? And you repeat all the way back to the system all the way until you solve back for x1. So this is what's called the back substitution. Right? So let's perform this back substitution here. For example, in this case, we have that 5x2 will be 31, right? Where did I get this from? I got this from the bottom line of this augmented matrix. And so I perform this formula here. So x2 will be 31 over 5, whatever number that is. Now I take this number here and I plug it in up there, right? So now our new equation will be 2 minus 6 times 31 over 5 equals to minus 18. Right, sorry, this should have been, let me find an eraser. This should have been 2x1, right? So this is going to be 2x1. Right, so that's more like it. So now we take this number here and put it on this side and then divide by the coefficient, right? So it's exactly what this formula is saying here. So let's do that. So this is x1 will be minus 18 plus 6 times 31 over 5 divided by 2, which is this formula here. So here is, the summary of this procedure. There are 2 parts: the forward elimination procedure and then the backward, right? So the first part, you iterate, you do this n-1 times, right? So here you're going to rewrite those equations and you're going to substitute each number in that augmented matrix by this number instead, as we just talked about, right? And of course, you do the same thing for the right-hand side. And this procedure will give you a new augmented matrix, but one that has been where the values below the diagonal have been set to 0. You then start the backward substitution by assigning the value of the last unknown, right? That was easy. And then you substitute, first you compute compute the sum, right? To start with the sum as said over here, and you keep adding to the sum this negative value, right? And at the end, you just divide the sum by the right pivot, and then you got the solution for that particular variable. So one issue can come up here, right? And the issue is here, what if the pivot, in this case, is A11, right? So we're looking at zeroing out all these elements, so we take the A11 as the pivot. What if this guy here was 0, or even close to 0, right? But if it was strictly 0, you have A21 divided by 0. What sense does that make? Right? None. So we can't have division by 0. If we do have division by 0, the whole procedure will fail. So what can we do? Here is where that first rule we talked about what can we do to this linear system that doesn't change the solution, is reverse the order, right? So I can, if this pivot point here, which in this first row is A11, if this is 0, first, what I can do is I can search and look at the other equations. Is there any other equation where the front number here is not 0? And if so, I can just put that equation to be the first one instead and solve this rearranged system instead, right? This will avoid us dividing by 0 and may still allow us to find the solution to the linear system. Of course, I don't do that just for the A11 procedure. When I'm zeroing the values below A22, for example, I do the same thing. I look below and see if A22 is 0. I look below and see if there's one that is not 0, and I modify that system, right? So, and you can do this for any pivot point. This is known as pivoting, and it's a good thing to do to avoid issues with division by 0. And as we talked about at the beginning of the video, there are some systems that may have a solution, a unique solution, but may be hard to find, numerically difficult to compute. And one number, one gauge that we can use to see how difficult a linear system is to solve is the so-called condition number. And the condition number is defined as the matrix norm, the multiplication of the two matrix norms, the original system, the original matrix describing the linear system, as well as the inverse of that matrix. This norm multiplied together is known as the condition number. Systems that are difficult to solve, where the lines are close to being parallel, have condition numbers that are much larger than 1. And they indicate again that these lines are close to being parallel. So here's a particular example, right? So let's say we have this linear system here, where the A matrix is this one, and the B matrix is that. The condition number is 4003. The real solution to the system is 2 and 1, right? But let's say, because I'm storing these numbers with binary representation in a digital computer, let's say for some reason, instead of storing 1.001, stored as 1.002, right? We rounded to that for some reason. Then the solution of that is not going to be changed by 0.002. It will change by 0.5 in both directions, right? So these systems you have to be careful, and perhaps these systems you have to be especially careful to store the numbers of the linear system to as much digital precision, or as many bits as possible. Finally, I'll mention that this Gaussian elimination procedure for solving linear systems is computationally expansive, and more or less it scales with the order n cube, where n is the size of the system, right? So we're solving an n by n system, the same number of equations as unknowns. So the cost of this, the number of floating point operations, or real value operations, is on the order of n to the cube, right? So for example, if you're solving a system that has 10 equations and 10 unknowns, this will cause you to spend more or less 667 floating point operations. If you instead solve a system for 100 unknowns and 100 equations, right? You multiply the unknowns by 10 only. However, you have really increased massively the number of operations that you need to use to perform. So Gaussian elimination is not that cheap to compute. It's very fast on a regular computer for small systems, but as the systems get larger and larger, it tends to slow down quite a bit.